Welcome to Ask and Learn.
In this problem, we are going to analyze an AC circuit, specifically find a couple of unknown currents that are running through two different components, a capacitor, I2, and the diagram is running through a capacitor, and I1 is running through an inductor, and there is a resistor that is in series with the voltage source, which is an AC source. Now, what's nice about this situation is that the components inside the circuit are already represented in phasor form. So we are going to be using phasor algebra and normal circuit rules, namely reduction into equivalent impedance in this case, not resistance, and some junction rules. And specifically, there is one junction we'll be looking at where the current splits in order to find those unknown currents. But this is the nice thing about AC circuits, is that the Kirchhoff's rules for loops and junctions still apply. Reduction of resistances by using parallel and series concepts still apply, but you have to use the concept of impedance instead. Phasor algebra, as a reminder, is algebra on imaginary or complex numbers in the complex plane. So a reminder that you can think about two different components of the things in the circuit. There are real parts of each component and imaginary parts of each component, and therefore components such as currents, voltages, and even impedances have a real and imaginary part. They also have a magnitude and a phase. Okay, so the magnitude, if you have a complex number, is just the hypotenuse in this imaginary plane, and the phase angle represents the angle that that component makes to the real axis. And I won't say too much about it other than the voltage source. What we know is it has an amplitude of 40 volts, and it has a phase of 0 degrees. So it would lie completely along the real axis. But let's not get too much into the algebra. What we see is that there is a parallel branch, which I will lightly outline. So we have two resistances, or impedances, we should call them, in parallel. And let me be more clear and call that Z parallel. And we're going to find that in the usual way, by taking the inverses of the impedances and inverting that. And all this is going to be algebra on complex numbers. I'm not going to write in units. That could get a little confusing, but what we're basically doing is taking the impedance of the inductor. Oops, and I promised I would not put in that unit. We're taking the impedance of the inductor and the impedance of the capacitor and putting them into a usual parallel type of situation. And so what we're trying to do is find a Z total, and then we can figure out the I total as the voltage of the source divided by Z total. We're going to use the junction rule. I'll show the junction again. Junction. That I is the sum of currents coming out of it, which is an I1 plus an I2. And we can use a parallel arrangement to separate out the I1 and the I2. So these are 4 steps that we're going to have to take in order to analyze this circuit. Okay, and I may not go through all the little steps in gory detail, but what we basically have is I1 times 5J. So voltages on the 2 parallel elements should be the same. So I1 times 5J should be equal to I2 times minus 10J. Voltages in parallel are always the same, is what we're saying there. Okay, so here's step 1. We're finding the Z parallel. I will jump ahead with some of the, well, I'll go ahead and show some of the steps so you get a feel for that. That would be 10 minus 5 over 50J to the minus 1. And that turns out to be, after you flip everything around, 10J. So that parallel then is in series with the 8 ohms. So our Z total is 8 plus 10J. And now what we want to do is convert that into phasor. Well, actually combine it with the voltage source, which is in phasor form. But it pays to convert this into phasor form to begin with. That is 12.68 at an angle of 51.3. And a bit of a reminder, an aside on how to do that. The magnitude comes from taking 8 squared plus 10 squared, and the square root of that, you get 12.68. The tangent of the phase angle is equal to the imaginary part divided by the real part. And so the phi is the inverse tangent of 10 over 8, 51.3 degrees. Let's put a degree by there. Okay, so now we can find the total current. What we're going to do is take our voltage, which has an amplitude of 40 at an angle of 0, and divide it by 12.68 at an angle of 51.3. Now, how do we do that division? Amplitudes just divide. So we get a new amplitude. Angles are actually up in a complex exponential, and so they actually add or subtract depending on whether you're multiplying the exponentials or dividing them out. Here, because we're dividing by a 51.3, that gives us an angle of minus 51.3 degrees. So now we have our total current in phasor form. What we're going to have to do next is use 3 and 4 to break this down into individual currents. And it doesn't matter who you substitute where. Well, it does, but as long as you're careful, it should work out. What I am going to do is I am going to substitute, let's see, I2 into equation 3. So we're going to sub for I2 by using equation 4. We find out that I2 is equal to minus 1/2 times I1. And the J's nicely cancel. That's always kind of cool. And so we can write our new algebraic expression. I is equal to I1 minus 1/2 I1, doing that substitution, which is 1/2 I1. So this tells us that I1 is twice I. If we work it out, I1 is equal to twice I. And that's easy enough to do. We're just going to multiply the magnitude. So that's 6.30 at an angle of minus 51.3. And I2 is going to be negative 1/2 of that. Okay, so we're going to go back to our substitution, and that gives us minus 3.15 at an angle of minus 51.3. And those currents are in amps, so no tricks there. Now, to convert back, these are in phasor form, and it helps to do one more step, which is number 5, convert currents back to time domain. And just a reminder that the Vs at 40 volts at 0 degrees, basically there's a couple ways to write it, but I like the cosine base. So that would be 40 volts times cosine of omega, which in this case is 120 pi, times t plus a phase of 0, which we won't write in there. So if we write down I1, we have to use the same function, but that would be 6.30 amps times cosine of 120 pi t minus 51.3 degrees. And I2 then would be minus 3.15 amps times cosine of 120 pi times t minus 51.3 degrees. And you can check this out pretty quickly, but it's nice that I1 and I2 will add to give us I very readily, both in phasor and in time-dependent form. Yeah, so I should be equal to I1 plus I2. And we have the same cosine function, so we can just add those up. 3.15 amps times cosine of 120 pi t minus 51.3. And just one last statement. Many people would be disturbed by the fact that I1 has a larger magnitude than the big current that's supposed to run through a battery. And this just points out that AC, these things can happen. And they can happen because your inductor and your capacitor are both storing energy during a cycle. And so you can get these interesting phenomena where you have voltages that can be larger than 40 volts, and you can get currents that are greater than the current that runs through the voltage source. So something to be aware of.